Okay, just like Alistair mentioned, I'm going to be exploring the coexistence of a CAM-shrub and C3-tree in the bad word, subtropical thicket. Okay, so we have this situation in the evergreen subtropical thicket or succulent thicket, depending on where it goes, where we have CAM and C3 photosynthetic plant dominance. And then we have this unusual situation where the CAM plants have a high abundance as well as high biomass. And so we postulate that this might be because of the unpredictability of rainfall in the subtropical thicket. So this is why I've explored this thing of coefficient of variation of the mean annual precipitation, where if you have CV less than 20%, it's low. CV between 20 and 30 is moderate, and then CV above is considered to be high, and then the subtropical thicket is sitting at about 40%. So this is one of the components that we felt we needed to explore the water use of these two functional types. And then we also, how we're going to go about, or how we've tried to go about exploring this coexistence is using Walter's two-layered hypothesis. How am I sounding in the mic? I feel like there's a lot of... Okay. So Walter's two-layered hypothesis, which it developed for semi-arid savannas. Basically what it says is that, semi-arid savannas to explore the coexistence of C3 grasses versus C4 grasses versus C3 trees. What this says is that the grasses are going to have their roots in the upper layers of the soil, and then as soon as it rains, they're quickly going to use up that water, whereas the C3 trees are going to have their roots running further down, and they basically have exclusive use to the deeper waters. So why we went about it through Walter's two-layered hypothesis is that it's been used in deserts, semi-deserts, and dry steppes, and then it's also been used in semi-arid ecosystems, even though it was developed for semi-arid ecosystems. So our working hypothesis at the moment is that the CAM, which in this sense we're going to be using spectrum, they're going to have their roots in the upper layers of the soil, whereas the C3, they're going to do a similar thing as the trees in the savannas. These are just the aims and objectives. So determination of water use patterns in CAM versus C3, and then we want to see how do they respond to changes in rainfall and extended dry periods or droughts. And then we're going to look at the phenological states. Basically, when do the leaves and the stem start to grow, and then look at when flowering starts. And then a big component is the root niche partitioning, where we want to look at the proportions of the CAM versus C3 roots along the soil water profile. Study is being done at one of Hive Ecosystems farms. So for the water use analysis, we're going to be using this thing called a dendrometer. So you basically tie it around your stem, and then it measures stem variation using voltage. This is just from the supplier of the dendrometer. And then this is our setup at Hive, where we have our dendrometer down here, and that's just a data logger. And then at each, we have one connected to a spec boom and then another to a papier. And then this is a trail camera just for looking at the phenological states. This is just a conversion formula to get your voltage data into circumference. Okay, so we've been doing a lot of digging at Hive. I'm sure Yappy has noticed. So what we tried to go for is a situation where you have your CAM component and your C3 component. So that's just a euclid and a spec boom. And then we did pits under the canopy. away in the open and then between the canopy. Okay, and then once we have these pits, I had to go in and then dig in 5 centimeter intervals for the first 25 centimeters. I collect the soil that I collected from that interval of 20 centimeters by 20 centimeters by 5, and then going down, we start at 10 centimeters up until we hit the hard pan. We were hitting the hard pan at about 45 centimeters at at Hive. And then once I have the roots, I have to separate. Once I have the soil, I have to now go and look for the roots. And then the roots that we targeted were the roots that are less than 2 millimeters, because we believe those are the rain collecting roots. So we care about, well, we're trying to look at the water use of these plants. And then once I'm done processing the roots, I'm going to send them over to UCT for stable isotope analysis, which is actually going to tell us when we have this, as we're going down, are we picking up basically CAM, and then C3. Okay, and then that's just one of the models I'm going to use to see if there's overlap between the roots or not. I recently just got these from Alistair yesterday, from Professor Kathy Clark, who, after we told her about our study, actually went digging. And then this is what you see, actually. Speckworm generally forms this carpet of, and you can see also it's fine roots on the upper layers of the soil. Whereas when you start going down the soil profile, so these white looking roots there, that's mostly speckworm. And then you start seeing these dark looking roots, that's the euclea. So you could kind of see you can see signs of root niche partitioning just from that observation. Okay, and then these are the graphs that I've plotted so far. So this is what the papias are doing when you're looking at the dendrometer data. So you can simply interpret these as this is shrinkage, and that's expansion. Shrinkage, expansion, shrinkage, and expansion. And then the shrinkage and expansion, it's usually associated with periods of when there's no water, they go through that, and then once they start to get water, they start expanding again. This is what the speckworm is doing. And then these are the graphs put on top of each other. So you see what the papia is doing, and then that's what the speckworm is doing. And then I've just added the rainfall data. I'm still waiting to get rainfall from the weather stations at Hive, but this is I got from NASA Power, if I believe. So you see here, after a rainfall event, you can see the papia is starting to spike, and then there's no rainfall in this period. It's shrinking, more rainfall, it spikes again, goes down, bit of rainfall, it spikes, and then you look at the same thing for the speckworm. When it hits a rainfall event, it also spikes, goes through a bit of a drought period, it goes down, and then more rainfall events, it spikes again. And this is what you have when you have them together, the speckworm versus papia. But you also start to notice this trend where in situations like this, where the speckworm is actually not losing as much water as the papia. Well, that is, I believe, because since speckworm is a CAM plant and they better adapted for semi-arid regions, which is why you see it's consistently riding above the papia. Okay, and then this is just a better way of actually showing the shrinkage versus the contraction versus expansion. And then you can actually use the data from dendrometers to tell you when are these plants actually growing. So you have these periods of increment. So if I were to run a line from there to there, you see that it got a bit of increment and then nothing there and then increment. And this is what you have when you are looking at the papias versus the speckworms. Oh, sorry. This I still have to see if I might need to actually detrend the data or not, because this is from just after the dendrometers have been set up, so I don't know if they've settled or not. But this is basically a representation of what these trees are doing. And you see that with the speckworm, you are seeing more areas of consistent increment versus the papias, who do not seem to be going through any increment in this side. Okay, and that brings me to the end of it. I just want to thank Professor Potts and his family. KK is going to be presenting in a while. She helped me out in the field. Margot and Manda for the late nights of processing data. Hive and Yapi for allowing us to work at their farm. Thank you. Have any questions?